5 is solving logarithmic and exponential equations. So we'll do that. And then we get to do some graphing. Graph ellipses and hyperbolas today. So we will do all three of the conics. We'll do the ellipses first, and then we'll do the hyperbolas, and then we'll do the parabolas last. Parabolas, you already know how to graph a parabola using sort of the a times x minus h squared plus k method. And then when we graph parabolas as conics, we do it slightly differently. But parabolas are going to be last. We'll do those last. Ellipses should be the easiest of the conics to graph. They're just, it's just like a circle. And then hyperbolas tend to be the most complicated. But we'll spend enough time on it. It will go fast, though. We'll spend just enough time. All right, so let's talk about solving equations. And for both exponentials and logs, we have these two equality statements. If we have two exponentials that are equal and the bases are the same, that means the exponents have to be the same. Pretty intuitive thing. So if we, all that's saying is if we have something like 2 to the 5 equals 2 to the x minus 1, that just tells us that the exponents have to be the same. And so that gives us a way to solve. So that's a pretty simple exponential equation when you can do that. And it's very rare in practice that you will be able to do that, but if you can, that's definitely the first way to go. And the same is true with logs. We have something like log base 2 of x minus 4 equals log base 2 of 3. The equality principle here can be used. If we have two logs that are equal, set equal to each other, and the bases match, then the arguments have to match. So those are two simple equality principles that we'll use. In this first one here, we can use that principle. It's not immediately obvious, perhaps, but we see that on the right-hand side here, we can rewrite 27 as 3 to the 3. So then we can use the equality principle for exponentials, and this tells us that our exponents have to be equal because the bases are equal. So this tells us that 7x is equal to 3, so x is equal to 3/7. Okay. Similarly, with number 8, how are we going to rewrite 16 so that we can use the equality principle for exponentials? Yeah, we're going to write that as 4 squared. Right? So if you can equate the bases, then it's a pretty straightforward problem. You set the exponents equal to each other and carry on your merry way. So does anyone have any question on that? Those will be probably the simplest types of equations that we'll see where we can actually use that equality principle for logs or for exponents. Yeah, you can put it there. Put it there. All right, let's go to another one. We can use the equality principle for these two. Well, at least the one on the left. A little more complicated, though, because we have a fraction, and when we have a fraction, we'll have to use a negative exponent. And our goal will be to try to rewrite the right-hand side so it's 3 to some power. And what would that power be?
Negative 27.
Not negative 27. You're on the right track. The exponent has to be negative. Negative 3. Because that will give us the negative exponent creates a fraction. That's going to be 1 divided by 3 to the 3. 3 to the 3 is 27. And that allows us then to use the equality principle for exponentials. We can say that x squared plus 4, x is then equal to negative 3. 3 here. And I want to make a statement here, or just point something out. Really important, the common mistake, and I forget what test, we had one test where we were solving some equations. And the most common mistake here is to, and it gets you nowhere, but I see it all the time. When you have x squared plus 4x equals -3, to factor the left side here, and then say x is 0 or -4, right? That does not work. If you want, our goal is to use the zero product rule, and the zero product rule says that if we have something like AB equals 0, then either A or B is 0. So to use the zero product rule, we need to have a 0 on the right-hand side of the equation. So we don't want to factor. We want to move everything to the left. And this is a general principle for solving nonlinear equations. When you have a nonlinear equation, everything goes to one side and you factor. That's how you solve a nonlinear equation. Everything to one side and factor. Okay, different from a linear equation where you put the letters on the left and the numbers on the right. Okay, so we have to move the 3 over, nonlinear equation, so set it to 0, and then we factor. And this tells us that our solutions, and sometimes they're only potential solutions, it depends on kind of how we got to those answers. And you don't have to do a formal check. But when we come back up here and look, we just sort of make sure that there's no major issue. With this type of exponential, there's not going to be an issue. But if we took the log of both sides and then used the log property, something might happen that would force us to exclude one of these answers. Now, given that this is an exponential, there's no problem having a negative in there for x. No problem at all. But with logs, sometimes negatives will not work. Okay. So again, that's going to be the easiest type of exponential equation if we can set it up so that we have the bases the same. Now over here, we can't do that. This is more kind of common when you have an equation that you can't, it's not going to be so cooked up most of the time. And here is the fundamental property of logs that make them really powerful. Exponential functions are functions where the variable is in the exponent. And we want to solve for that variable. We want to know what t is. And this is what logs enable us to do. We can take the log of both sides, and typically we take the natural log. If we take the natural log of both sides, the property of logarithms that we're really trying to target here is the power rule. The power rule says that if we have the log of an exponential, that power can drop in front. So this is how you can solve for an exponent. Most important practical application to a log is that it allows you to bring an exponent down and you can solve for the exponent. And there's all sorts of applications like this. When you're looking at compounded interest and you want to know, hey, when's my investment going to triple? You're trying to solve for t, which is up in the exponent position. There's lots of other applications like that. Population growth and population decay, radioactive decay. Where you're trying to figure out when something will meet some sort of condition. And all those applications, they're modeled with exponential functions, so you're trying to get that exponent down so you can solve for it. And that's why logs are so important, because they allow us, the next step here is we can bring that negative t down. And here we have a cancellation property that we can use, so we can think of this in one of two ways. We could use the cancellation property. We have a log with a base of e, there's a hidden e down there, so those are going to cancel, and we're going to be left with negative t. Or you can think of bringing the negative t down in front, and then log base e of e is 1. So there's two ways you can think about that. And then we multiply both sides by negative 1. So t, this would be an exact answer. And if you wanted an approximation, you would type it into your calculator. Sometimes in algebra books, they love to use log properties unnecessarily just to kind of mess with you, I think. You could say, hey, I'm going to make this 4 100ths. You do that, right? Which is 2 50ths, which is 1 25th. You do that, and then I could bring that negative 1 up as an exponent. We're going to follow that. 0.04 is 4 100ths. 4 goes into 4 once, 4 goes into 125 times. So 4 100ths reduces to 1 25th. That power rule going backwards, here we brought the power down. Here we can take the coefficient up as a power. And then what's 1 25th to the negative 1? 25, right? Yeah. So there, if you're looking at an answer that you have and it's not matching an answer that my math lab has or the back of the book has, check your log properties, because quite often they're going to try to manipulate things to make it, if you can get rid of the negative, a lot of times they like to get rid of the negative. If you can get rid of the decimal, they're going to try to do those things. But again, that's an exact answer right there. If you want an approximation, you would type it into your calculator. That's exact. That's exact. All right, let's. When you guys try 24, 24 is one that you should be able to do after what we just did. Let's see if you can muscle your way through 24. Very similar to the last one, because you're trying to solve for a variable that's way up in the exponent position. You're going to have to do something to bring that variable down. Now remember that the ln function doesn't distribute. You have to isolate your variable term before you take the natural log. You don't want to take natural log of a minus b, because that's not natural log of a minus natural log of b. So you want to isolate your variable term with an equal sign between the two before you take natural log. Once you isolate the variable term, then you can take natural log, and then your exponent's going to jump down. And then solve for x. So our first step, we'll add the 1.87 raised to the x to the other side. I'll leave it on the left just because it's got the variable in it. So we want to do that first. Isolate the variable term. And once the variable term is isolated, then we take the natural log of both sides. That allows us to pull the exponent down as a multiplier. Then we can solve for x. So there's the exact value for x. That's exact. It might not look very precise, when you type it into your calculator, that may feel more precise, but that is exact, and when you type it into your calculator, you're getting an approximation. And now there's no log property that we can apply there. A log divided by a log cannot be rewritten with a log property. All right, let's go for 26. 26 is a little tricky. We're going to move the 1 to the left. Now that negative exponent, it's a trinomial looking expression. We would love to FOIL it. Maybe I should say unfoil it. Factor. But that negative exponent is not helping us. Most of us aren't going to be able to factor that in a neat way, in an intuitive way. But we can get rid of that negative exponent. If we multiply both sides of this equation by e to the x, let's notice what happens. So if we multiply e to the x,
That first one's supposed to be.
yeah, that's an e, sorry. Not a 6 to the x, so that's an e. So we're going to multiply everything by e to the x. Then our first term becomes e to the 2x. E to the x times e to the x. We're multiplying exponentials with the same base, so we add the exponents. And then what does negative 6e to the minus x times e to the x get us? What's e to the x times e to the negative x? If we say e to the x, and we multiply it by e to the negative x, we add the exponents. What's x minus x? 0. So we end up with, yeah, just 1. When we multiply by e to the x, that's going to be 1. And then we multiply 1 by negative 6, we get negative 6. I'm going to just slide that over to the C position. A, B, and C, I'll write it over there, C. Because then I see that e to the x times negative 1 is going to pull back another e to the x in there. So then we have that expression. And that's just a quadratic. It's slightly disguised, but you can factor this in the same old. This 6? Yeah. So negative 6 times 1. So when the e to the x is multiplied by e to the negative x, that gives 1. So we get 1 times negative 6, which gives us the negative 6. And then e times negative 1 is going to go this way. I'm just reordering it so that it's in kind of equivalent to descending ordering.
Oh.
I heard a light bulb. And this factors. This can, in fact, be unfoiled. Because we know e to the x times e to the x is e to the 2x. So that's first, right? That matches first. E to the x times e to the x. And now we're trying to have two numbers multiply to negative 6 and add to negative 1. So two numbers that multiply to negative 6 and add to negative 1. Minus 3 plus 2. Let's check. The inner is negative 3 e to the x. The outer is positive 2e to the x. Negative 3e to the x plus 2e to the x is negative 1e to the x. So that matches. So we've now factored it. So this tells us, using the zero product rule, we have two factors that are multiplying to 0, so one of them has to be 0. This tells us that e to the x is equal to 3, or e to the x is equal to negative 2. Zero product rule. Our whole goal, of course, is to solve for x. We're always solving for x when we're solving equations. And we get all the way to x. And from this first equation here, what is x equal to? What does that tell us about x? What do we do to both sides there to solve for that exponent? Natural log of both sides. And natural log of e to the x is just x. And then on the right side, we have natural log of 3. So that's one solution. Now how about that second equation? E to the x equals negative 2. Say that again?
Natural log of negative 2.
So we can take the natural log of both sides, that's fine. And then what's natural log of negative 2? Here's a picture of a typical basic log right over here. Verticality to here. What should we conclude from the natural log of negative 2? Undefined, right? Because the natural log function, as any basic log function, is only defined if the x's are positive, if they're to the right of 0. So natural log of a negative number is undefined. So here we have no solution coming from that side. You can also see that in the line above, where it says e to the x is negative 2. If you take a positive number, b is 2.7-ish, and you raise it to a power, can you raise a positive number to a power and force it to turn negative? No. All right, if you take, say, the number 2, and you start multiplying it by itself, does it ever become negative? No. Even if you put a negative exponent, right? If you did 2 to the negative 1/2 or something, still is not becoming negative. It turns into a fraction or a square root. But you can't turn a number negative by raising it to an exponent. Its base is positive and remain positive. So that part has no solution. So our only answer there is x is ln of 3. All right, so why don't you guys try 28? And you might need the natural log. Both exponents would jump down in front and multiply. This is parentheses around the x plus 1. Yep, that's right. That's the first step. Not done. That's your first step. First step. Yep, except parentheses around the x plus 1. Because that ln2 will distribute, so it will distribute to the 1. So once you get those exponents down, you have to collect like terms. So you've got to get all the terms with an x to the left and all the constants to the right. So the natural log function doesn't distribute. Nope, so you cannot take the natural log of that. So it doesn't distribute. This is going to get you messed up. Then you can isolate your x with favorite F word. So a lot of you got to that step there, and here, it may not look like it, but isn't that a linear equation? Like the exponent on the x's is 1. Both those x's have an exponent of 1, so that's linear. And our general principle for a linear equation is expand everything so that you don't have any parentheses, and then collect the x's to one side and the numbers to the other. So here what we'll do is distribute that natural log of 2. And then we have two terms that have an x in them. So those have to be grouped on the left side of the equation. And we have one constant term. ln of 2 is a constant. That's going to go to the right side of the equation. And now on the left, we can collect our x's. And then how do we consolidate those x's? Right now we see x appearing in two terms. How do we deal with that? Factor, right? So we'll factor that x out. So that's going to be x times ln 2 minus 2 ln 5 equals minus ln 2. And then our last step. Question, Richard?
I was just the ln on the second line right there. What is that?
Here?
Next one.
There?
Yeah. Oh, ln 2, I'm sorry.
So yes, minus ln 2, so that positive ln of 2 on the left, that's going to move to the right and become negative. So we're going to take that, it's a constant, so we want to shove it over to the right. Put the constants to the right. And what's our last step then? All we have to do is divide. And on the test, this is a totally fine answer. Nothing wrong with this. Now, if you're looking in my math lab or in the back of the book, they're probably going to do some combining here. Again, I would be fine with that answer on a test, unless the instructions are asking you to apply log properties and condense a log expression as far as you can. That's a totally fine answer. But you could do some things like this. You could make the numerator natural log of 1/2. And in the denominator, you could make this natural log of 2 minus natural log of 25. And then from there, you could make this natural log of 1/2 over natural log of 2/25. Could do that using log properties. And then there's nowhere to go. Here, you can't, there's no log formula if you have a division of two logs. Adding and subtracting? Yes. Dividing and multiplying? No. Yeah? Okay, so good question. So the minus sign out in front can come up as an exponent, and then 2 to the negative 1.
Oh, it comes out. Okay, I thought it was 2.
Yep, so it comes up as an exponent on the 2, not as a multiplier. So that negative 1 comes up into the exponent position, and then 2 raised to the negative 1 is 1/2. Let's see if you can do this one. So this one is very similar to the other one we did with the e to the negative x. Move the 4 over and multiply by e to the x. See what happens. See what happens. Yep, exactly. e to the e to the x times e to the negative x is e to the 0. Yes. Oops. All right, let me jump in here then. Before we don't want to, the quadratic formula, if you need that, that's going to be a little messy. Let's get to the important point first. So first, multiply both sides by e to the x, or subtract the 4 first. It doesn't matter which order you do it in. Does everybody see that that's what it looks like after you multiply by e to the x? You're multiplying the entire equation by e to the x. E to the x times e to the x is e to the 2x. E to the x times e to the negative x is 1. So this is going to be e to the 2x minus 4 e to the x plus 1 equals 0. All right. Now, because this does not factor, the only way to factor that 1 is negative 1 and negative 1, if you're going to get a negative in the middle, and that doesn't work. So you'd have to use the quadratic formula here. And I don't want to spend time doing that right this second because it's a little bit time consuming. I'm not going to give you one this complicated on the test. But you would use the quadratic formula there. It's a little messy, but we don't need to go through that extra detail. Bigger fish to fry right now. All right, so let's go to a couple more. So these log equations, we're going to kind of go through the same process. First, we solved exponential equations where we could use that equality principle. And now we're going to see if we can use the equality principle or use a basic rule of logs without getting too complicated. Now, this first one, we can rewrite this log using the definition of the log. The definition of the log said that you could convert a log equation by saying the inside of the log, the argument of the log, is equal to the base of the log raised to the other side. So that is using, we would say that that's using the definition of the log. The definition of the log is what allows you to take a log and rewrite it as an exponential. And so we took this log equation. Other side of the coin is the exponential form. Every log form has an exponential form. We convert it to the exponential form, and then we're done. Same idea here. What's the base on this logarithmic function there? Base is e. So here the argument, the inside, is going to be equal to the base, raised to the other side. Not much you can do here. Some would prefer that exponent to be positive. On a test, doesn't matter to me which of these forms you write it in. X is equal to 1 over e squared. Okay, here, x is already isolated. We already have x. But we need to try to simplify that thing right there. We'll try to figure out how to simplify that. Maybe it is, if it's not obvious, which it's pretty unobvious, I would think, for most of us to look at that. Sometimes it's beneficial to go to an exponential and play around with an exponential and then come back. That sometimes works. If it's not obvious how to simplify that, like if it was something more intuitive, you could just jump to it. If you had something like log base 3 of 1/9 or something, where you could say, oh, okay, that's the power of 3 down there, so what would the answer there be? 3 to the Yeah, so the answer would be -2 on the right, exactly. 3 to the -2. So if you have something where you can kind of do it in your head, that's fine. If you can't, then fiddle around. Let's say, oh, okay, well, this is kind of messy, so I could rewrite this as the inside is equal to the base raised to the other side. Could be that. And all of a sudden, it might look a little more manageable because you should see that you could write both sides as an exponential with a base of 5. Everybody agree with that? How do you write 1/25th with a base of 5? 5 to the what power? 5 to the -2. Good. And then how can we write 125? 5 to the 3. Yep, exactly. 5 to the 3. X is still there. And now we're using the equality principle for exponentials. We get x is equal to -2/3. Yeah. Not so obvious when you look up here that 125 to the -2/3 is 125. Definitely not obvious. All right, let's get over to this guy. So this is a really typical traditional log equation. And what we're going to do is combine our two logs. So if we're adding two logs together, the product rule for logarithms says that that will be the log of the product of the two arguments, two insides. So inside here we have x squared minus 1. And now I'm going to apply the definition of the log. Definition of the log says that the inside, the argument, is equal to the base, which is 2, raised to the other side. Now we have x squared is equal to, what's 2 cubed? 8. And then we add 1, so x squared is 9. So x is equal to -3 or +3. Now here, we absolutely need to do a cursory check. With exponentials, it's rarely, if ever, an issue. With logs, there's often an issue. We started with the log equation, then we used the log property, and blah, 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 we came down to this point. And it's not that we have to go check every detail, but what we do have to do is make sure that we're not trying to take the log of a negative number or 0, because that's undefined. Logs are only defined for positive numbers. So when we look up here, if we plug in 3, we have the log base 2 of 4, and here we have log base 2 of 2. Totally fine. But if we plug in -3, this is negative and that's negative, so this guy is out. So our only solution is x equals 3. And so the checking is very cursory. All we're doing is making sure that we're not trying to take the log of something less than or equal to 0. Okay. You guys try 44. All right, so the first key is to do the division. The log of a quotient is equal to a difference of logs. That part's pretty straightforward if you play with the log properties. And then here's the equality principle. The equality principle says two logs that are equal, that have the same base, have the same arguments. And we're not dividing out log like it's a variable. We're using an equality principle. Log of a equals log of b means a is equal to b. We're not dividing that log. Technically, it's called, if you want to know, but I'll tell you, it's called exponentiation. The technical way to go from here to here, this is how we do it in practice, the equality principle. The way technically you would do it mathematically, if you really were wanting to do it step by step, you would exponentiate both sides, which means you put the left side as an exponent on 10, the right side as an exponent on 10, and then you get a cancellation property there. So if you were wanting to know that x would equal. In practice, we don't do that, but that's the property that we would use. So now here, I definitely saw a little bit of hesitation at this step. What we can do is multiply both sides by the x minus 3. And so on the right, now we get 2x minus 6. And then once you see that, you're golden. Then you say, okay, it's linear, x is left, constant's right. So we move the variable to the left, we get negative x. Move the constant to the right, we get negative 11. And so that tells us that x is equal to 11. And we have to check that. We go back up, and again, the check is cursory. We just want to make sure that the numbers that are inside are not 0 or negative. If they're both positive, we're good to go. 16 is good, 8 is good, we're fine. All right, so this one over here is very similar. We're going to do the same first step. Same first step. And so again, we now have the equality principle. Or if you want to get fancy, you would exponentiate with a base of 3. And that would cause that to cancel out. All right, so here's where it gets a little bit more complicated. We have that. Again, we'll multiply both sides. We'll clear the fraction by multiplying through by x plus 6. Well, x plus 14 equals x squared plus 6x. Collect like terms. Nonlinear equation. Nonlinear equation, everything to one side and factor. Always our plan with a nonlinear. Everything to one side and factor. So everything to one side and factor. This tells us via zero product rule that we get negative 7 or 2. Is negative 7 okay? Nah, not okay. Because you plug it into this log expression or that log expression, you're trying to take the log of a negative. That's undefined. So the only answer, and 2 does work, right? Positive, positive, positive. 2 is the only answer. Sugar, sugar, sugar. All right, you guys try 52. No. Dare. Don't you dare. No freshman dream. Oh, I see two X's. They must cancel. You should get to that point. Those X's do not cancel, right? Right, Ryan?
No, we're doing.
Oh, sorry. They do not cancel, right? Oh, you're right. Oh, in my other class. Oh, no. Yeah. I know. I'm looking at Alex and calling him. Come on, Alex. All right. So how do we do this? Next step. 4x, right? Multiply, and then we subtract. We get x equals 1/3. And is that number okay? Is there any bad? Nothing bad, right? It's all good. It's all good. We're not taking the log of any negatives. Or 0. Can't take a log of 0. All right, try 55. We're almost ready to move to graphing. Yeah, sure. Yeah. You tell me. What are we doing with the what are we doing with that x? So if it's linear, we want to combine it. So what do we do to both sides? Oh, okay. So we're going to subtract that x. Yeah, we're subtracting x from both sides. Equals 4x minus 1 is 2y. Oh, okay. This is yeah. Yes,
I
indeed.
knew it was there. I just.
Yeah, digging deep. Digging deep. Oh, all right, does anybody have a question up to that point? We combine the logs on the left, multiplication. We need to take the exponent on the right, or we need to take the coefficient on the right and turn it into an exponent so that we have a log equal to a log. And then we have our equality principle, inside equals inside. And then, pretty simple from there. Subtract x squared. And then we get 7x equals 8. So x is 8/7. And then we check to make sure that we're not trying to take the log of a number less than or equal to 0. Positive, 8/7 minus 1, is that positive? Yeah, that's positive. And on the right, positive, so that is our answer. Good. That's so bad, Kelly? Not so bad. Not so bad. Let's try a couple of more complicated ones. Actually, this one on the right is not so complicated. Let me just see how much further. Let's not do that one over there. We've done enough like that. Let's do 58. So 58. What do you think our goal is? What do you think our process will be here? We could do a natural log. That natural log is definitely would work because that's going to bring the exponent down. But there is a simpler way here because of the 256. We could write that as power 2. Everyone see that? 256 is 2 raised to what power? 256 is 2 to the 16? That. And then how do we bring that upstairs then? 2 to the 8? That 216 does seem a little large. Yeah, 2 to the 8, because 2 to the 4th is 16, and 16 times 16 is 256. So 2 to the 8, 2 to the 8. I agree. 2 to the 8. And then, how do we bring that up? 2 to the negative 8, whatever that exponent is. Yep. Now we use equality principle. We have x squared minus 9x equals negative 8. Non-linear equation, everything to the left in factor. Non-linear equation. Non-linear. And then that gives us 2 possible x's. And we should just look up at the original equation and make sure that nothing's wrong. If we plug in 1 up here, what's it, 1 in? So if we plug in 1, we get 1 minus 9, that's negative 8. So it's 2 to the negative 8, which is 1 over 2 to the 8. That definitely matches. And the only reason I'm checking a little bit more carefully here is because we've got that square. And quadratics, it's a little more complicated than if you just had a linear exponent. And then let's just check loosely with the 8. If we plug in the 8, 64 minus 72, that's negative 8. Yeah, okay, it matches. That's fine. And again, 99% of the time with exponentials, there's no issue. Logs are where we're going to see issues. So those are our 2 answers. The 2. All right, so these 2, we cannot solve algebraically, and so they're saying to use a graphing utility to figure out the answers. Let's just do that so that you're at least familiar with how you would solve. And let me make a comment. So if we want to figure out the x that satisfies this using a graphing utility, we have 2 choices. We can graph the left side, like y1 equals the left side and y2 equals the right side, and figure out where they intersect using your graphing utility. Or I think it's a little easier if you move everything to one side and you graph this. And then look for x-intercepts. Those would be the answers. Similarly over here, if we graph y equals x squared plus natural log of x squared, then we want to go look for the x-intercepts. That gives you a place to look. If you're graphing the 2 functions separately and trying to figure out where they cross, that can be a lot harder to kind of move around a graphing utility screen and figure out where they intersect. So usually what we would do is put everything on one side and then you're just looking for the x-intercepts. So if we wanted to do such a thing, which obviously you're not going to do on the test, but when you're doing your homework, this is a really great way to check. You can always check any equation that you're trying to solve. You can always check graphically. So we're going to do, oh my gosh, how am I going to remember that? 0.082. 0.082 raised to the 0.05x minus was it 0.34 or just 0.34? 0.034. Oh, did I not put a 0? I didn't put an e in there, did I? Let's get an e in there. All right. So does that look right? So now it's actually showing us the y-intercept. That's not what we want. So we need to stretch this out a little bit. So let's go over here and we want the y's to be
let's see, where am I going? I'm not going to the right place. There. What should I do with the y so I can kind of stretch it out a little bit? What should we go from where to where? Like negative 0.1 to 0.1 maybe? Would that stretch it out? Maybe that's going to stretch it out too much. All right. So that's what we're looking for right there. And do we think there would be one answer or two answers for this problem?
One.
Yeah, we think there's going to be one because it's not an x squared. Right? So one answer. So that would be our approximation to 3 decimal places. And again, you can always do this. If you're working on a problem and you're not sure that you used your properties correctly, you can always graph it and get that answer. All right. So that, again, is rounded to 3 decimal places. Let's do this one, x squared plus ln of x squared. X squared plus ln x squared. And let's start over. All right. So here it looks like we've got 2 answers. And is that negative answer okay? We have x squared in there, so we're expecting to get 2 potential answers. Is there any reason to cross out the negative one? No, right? Because it's going to be squared up here, so that's going to be positive. You okay with that? Yeah? Alright, so that's how we're going to do it using technology. We can't graph it. And again, any equation that you want, if you wanted to solve this one graphically, just subtract that, graph the left side, look for the x-intercepts. It's always a good way to check. You want to solve that one, subtract that, graph the left-hand side, check for x-intercepts. Always a good way to check if you're very confused at all. All right, let's take our 10-minute break, and then we'll do some graphing. Some graphing. So the standard equation for a circle, everybody familiar with that? Any question on the circle formula? The important thing here is the center is h and k, h comma k, and the radius is r. And so with this first equation here, we see that, okay, it's definitely a circle. We have x squared plus y squared. It's centered at the origin. And the radius is the square root of the right-hand side. Square root of 20, which we would reduce to 2 root 5. Now, if the circle is not centered at the origin, you often have to complete the square to find the center. So in number 10 here, we're going to group the x's. We're going to group the y's. And then what do we have to add to complete the square in x's?
2 over 16.
Close. Both. I hear everyone's real close. Divide by 2 and then square. Divide by 2 and square. So we take the 4, divide by 2, get 2 square, and we get 4. And then over here, divide by 2 and square. And if we add something to the left side, we also have to add it to the right side to preserve the equality. And this gives us x minus 2 squared plus y plus 1 squared equals none. So divide by 2 and square to complete the square. Then factor. And then identify center. What would our center be center there would be 2 and -1. The radius would be 3. All right, so those are circles. And let's go to an ellipse. See, the equation for an ellipse is very similar to the equation for a circle. Let me go back to the circle for a minute. With the ellipse, they force the right-hand side to be 0. To be, not 0, 1. So we would divide by 20. So if it's a circle, we leave the radius squared over there. But if it's an ellipse, we're going to divide both sides by whatever we need to make sure the right-hand side is 1. So if we had a circle, both these denominators would be the same, and we would typically write that radius on the other side. All right, so let's first talk a little bit more about the definition of an ellipse. With an ellipse, we have these 2 points called the foci. And a point is on the ellipse if the sum of the distances to the foci is constant. And so it doesn't matter which point I pick. If I come down here and I measure that and that, it will be the same. So what they're showing here is kind of a carpenter's trick. If you wanted to draw an elliptic arch, put in a couple of nails, put in a string of the length that you need, and then just trace that out, and that will build you an elliptical arch. And so that's kind of a confirmation that, oh, okay, so D1 plus D2, the distances to the foci, the sum of those is constant, no matter what. All the way around, some D1 plus D2 is always constant. All right, so in practice, when we graph this, what we want to look for are intercepts. And first off, where's the center here? The center is where? Center, anyone? Center? So let's go back to the circle for a minute. When we looked at our circle here, center is always with the squares. Right? The center is what's in parentheses below the squares. We had a 2 and a -1. And the center over here, we thought of it as x minus 0 squared and y minus 0 squared. So our center here is, origin. Right? So if there was an x minus 5 and an y minus 6, then we'd be at 5, 6. So you're looking into the denominator for the intercepts, not the center. So the center is going to be at the origin, and then we're going to do the intercepts. So if I want the x-intercepts, what does y have to be for x-intercepts? 0. So the y's are going to go away for the x-intercepts. So if we cross that thing out right there, we let y be 0, then what does x have to be? Plus or minus 5, right? So that tells us our x-intercepts. We cross out the y, x has to be plus or minus 5. And that pattern is always going to be the case that we're going to look below the x's. We're going to look below the x's to get the x-intercepts. If we want the y-intercepts, we let x be 0, so then y is plus or minus 6. Those would be the y-intercepts. And so there's our ellipse. Almost circular. So this ellipse is supposed to be, let me draw it totally to scale. It's a little longer vertically than horizontally. Supposed to be. because we went up 6 and down 6 and left and right 5. So the major axis is vertical in this case. That's the major axis. The other axis is called the minor axis. And the foci always live on the major axis. And they didn't give us the equation of the foci yet. We're going to get that on the next slide. Right, so the equation for the foci aren't there yet. Let's just do it now because it's simple enough. So to get the foci always live on the major axis, and the foci are determined by this letter C. And what we're going to do is there's a Pythagorean theorem-like equation that we're going to use. To find the foci, we're going to set C squared equal to the difference of the denominators. For a hyperbola, C squared will equal the sum of the denominators. For an ellipse, C squared is the difference in the denominators. We're going to do the opposite of what the sign is. So C squared will be the big denominator minus the small denominator, which is 11. So that tells us that C is the positive square root of 11. C is a positive number because it's a distance. And so this tells us that the foci are root 11 from the origin, and they are always on the major axis. This number is somewhere between 3 and 4. 3 squared is 9. 4 squared is 16. So somewhere between there. So 1, 2, 3 and some change. So here's where our foci are. 1, 2, 3 and some change. Focus 1, focus 2. Those would be our foci. If you wrote the coordinates of those foci, you would say the foci are at 0, comma, plus or minus the square root of 11. That's where the foci are. Okay. This one. The key for a hyperbola or an ellipse is that the right side is 0. Right side is 1. So we divide both sides by 36. When we divide both sides by 36, we divide each term on the left by 36, and we reduce. So we get x squared over 4 plus y squared over 9 equals 1. Okay. And the process for doing an ellipse, we find the center, and where is the center in this one? Yeah, still the origin. There's nothing being added or subtracted from y or x. And then how far left from the center are we going? 2. How far right from the center? So those are the x-intercepts. We can get those by crossing out y, letting y be 0. Then x squared equals 4. X is equal to plus or minus 2. And how about vertically? 3. So there is our ellipse. That. All right, and then the foci are going to be on the major axis. The major axis is again vertical. Major axis is vertical because the bigger denominator is under the y's. The foci live on the major axis, and the foci are found by looking at x squared equals the difference in the denominators. So C will be the square root of 5. That's between 2 and 3. So the foci are about there and there. And if you wrote the equations, we would say 0 plus or minus 5. We wrote the coordinates for the foci. Any questions up to that point? here's the summary of everything that can possibly happen. Let's not look at that too carefully. It's a lot easier in practice than looking at that slide. The only thing I want you to really get is that the foci are horizontal if the ellipse is horizontal. Foci are in a vertical line if the ellipse is vertical. That's really the most important thing to get from this picture. You've got your center, both. Here, the number under the y's is bigger than the number under the x's. Here, the number under the x's is bigger than the number under the y's. That's really all you need to get from that. Let's do some, and we'll come together. All right, so we've got this equation. We don't know just looking at it whether it's a parabola, a hyperbola, or an ellipse. We don't know. Now, given that we're in the ellipse section, we're assuming it's an ellipse. But to get to the point where we can recognize the equation, we're going to have to complete the square. Bless you. So we're going to separate the x's and the y's and put the constant on the right. And what should we do next? There's one step to completing the square that we have to follow here that maybe some of you forgot. If we want to complete the square in x's, there is a step before we divide by 2 in the square. What is that step? Factor? Yep. So we factor the 4 out. Leave a gap. For the y's, we factor a 9 out. Leave a gap. So before you can complete the square, the leading coefficient has to be removed. It has to be factored to the front. Both of those. Now we can complete the square. So now we look at the 12, divide it by 2, and square it. And that gives us 36. And how about for the y? 16. Divide by 2 and square, we get 16. Now we have to be super careful. We have to preserve equality. We added something to the left, so we have to add something to the right. And here's where we have to be careful. We added 36 inside some parentheses. There's a multiplier outside that needs to be taken into consideration. If we were to multiply this all back out, we would see that, oh, we didn't just add 36, we added 36 times 4. So we have to add 36 times 4 to the right-hand side. 36 times 2 is 72, 72 times 2 is 144. We're going to add 144 to the right. Similarly with the 16. It may look like we only added 16, but there's a multiplier in front that has to be considered. So we really added 9 times 16. So that's also, that 144 also, right? All right, now we can complete the square. So 4 times x minus 6 squared plus 9 times y plus 4 squared equals 144. Almost there, not quite. What's one last step before it's in standard form? Divide by 144. So if we divide by 144, we end up with let's see, how many times does 9 go next 16? Is that what we said? So there is our standard form. Divide both sides by 144, cancel the common factors. So, what is the center for this ellipse?
6, -4.
Exactly. 6, -4. That's our center. Yeah? And are we talking about that plus 4?
Yeah.
So the factorization is right in here. So y plus 4 times y plus 4 will give us this. Does that make sense? You see? So it's a perfect square trinomial. Y plus 4 times y plus 4 is y times y, and then 4y doubled, and then 4 times 4. Okay. Perfect square trinomial. And that's the whole point with completing the square, is that you're turning your x expression into a perfect square trinomial. You're turning your y expression into a perfect square trinomial. So that's what the effect of completing the square does. All right, let's go to our graph. So we know our center, 6, -4. I'm going to move that over a little bit. 6, -4. So the center, 6, -4, there. Now we have to decide how far left and right we need to go from the center. How far left and right we go from the center? We look under the x's. That's our horizontal marker. We go how far left and right from the center? Square root of 36. So, and the number under the x's is going to dictate, the square root of that number is going to dictate the left and right movement from the center to find the vertices that are horizontal. All right, so we're going to go left and right 6. So that's here, and then over here. Now this is the major axis, because that denominator is bigger than the other one. So that's our major axis. And then how far vertically are we going from the center? 4, exactly, 4. From the center, we need to go up and down 4 from the center. So that gives us our 4 vertices, although some books don't like to call the endpoints of the minor axis vertices. Most books will call these the major vertices, and then those ones the minor vertices. This axis connecting vertically is the minor axis, so those being called the minor vertices makes perfect sense. This book only refers to vertices, meaning the major vertices, but a lot of books you'll look at will refer to minor vertices versus major vertices. This book just calls vertices, and they mean these two, the major ones. The foci live on that major axis. The foci are determined by looking at c squared equals the difference in the denominators. Oh, and that's where the 20 is. Yeah, so that's where your 20 was coming from. So c is equal to 2 root 5. That's the distance from the center to the foci. That number is between 4 and 5. So between 4 and 5 from the center, 1, 2, 3, 4. So right about there. On that focus 2. This way, 1, 2, 3, 4. Between there, on focus 1. So the foci will have coordinates. We're starting at the x value for the center. We're adding or subtracting 2 root 5. And the y value for the foci is the same as the y value for the center. So those would be the coordinates for the foci. Any question on any of the steps?
How do you get the center again?
So the center is the opposite of what we see. So once we have it factored, opposite of what we see up here is a positive 6. Opposite of what we see there is a negative 4. So we get that from the factorization after we complete the square. Okay. And then under the x's, how far left and right? Under the y's, how far up and down? Foci, difference in the denominators. Let's take a look at that one. All right, why don't you guys try to complete the square and put that in standard form? Complete the square. Oh, it's everything's there. Oh, catch up to you guys when you play. Pardon? Negative 9.
Plus 9 plus.
Oh, that. I didn't see that. Thank you. Yeah, so we're going to move that to the right side. Now I hear you. Yeah, so completing the square, what are we going to add into the x group? Just a 1, right? 2 divided by 2 is 1. Square it, we get 1. In the y group, 9. 6 divided by 2. Have it and square it. What did we really add to the x group? 9. So we have to add 9 to the right. What do we really add to the y group? We have 90 plus 54, so 144. So what numbers? Divide by 144. So 9 goes into 144. 16. 16 goes in there. 9. All right, now we're ready to roll. What's the sign? 1 negative 3. Opposite of what we see. 1 negative 3. center is down here, 1, -3. And then how far left and right do we go from the center? How far left and right? 4. Look under the x's, 16, take the square root, we get a 4, so we go 4 left and right from the center. 1, 2, 3, 4. 1, 2, 3, 4. And how far up and down? 3 from the center. And there's our ellipse. All right. Major axis, horizontal or vertical? Horizontal. The number of the x's is bigger. What is c squared equal to in this case?
Root of 7.
So we're going to, yes, exactly, root of 7. So we take the big denominator, subtract off the smaller denominator, 16 minus 9, which is 7. We're going to take the square root, so we get root 7. That's a number between 2 and 3, so we're going to go between 2 and 3 to the right, and 2 and 3 to the left of the center. 1, 2, 3, 4. And if we wanted to write the coordinates of the foci, all right, let's see. So we have to go root 7 left and right from the center of the ellipse. That x value is 1, so we're going to do 1 plus or minus root 7. And the y value for the foci, doesn't matter which one we're at, the y value is going to be -3 for both. Listen. Good? Not too bad. All right. So let's try to do one of these more abstract problems. I think drawing a picture is always helpful, so let's do that. You don't absolutely have to, but I think it's generally helpful. All right, so this says we have vertices, and by that they mean major vertices. So they're saying that, all right, this is our major axis. The foci they've given to us, 0, 4, and 0, -4. Okay. We want to find the equation. Let's see. We know the center. Center is the origin. So we know that we're dealing with x squared, and we're dealing with a plus and y squared. We know that side. What number can we fill in next? Can we fill in the number below the x squared? Below the x's? Below the y's, yeah. So the number below the x's, we're a little ambiguous, right? Because we don't know how far left and right, but we know up and down we're going 6 up and 6 down, so we square that and get 36. So that's below the y's because that's our up-down movement. Now we have the foci are 4 units from the origin, so that means that c squared is equal to 16. All right. And the big denominator minus the small denominator is giving us that 16. We know the big denominator is the vertical one because that's the direction of the major axis. So it's got to be 36 minus what gives 16? 20. Follow that? So it's the big denominator minus the small denominator gives us c squared. C squared is equal to the big one minus the small one. So there's our equation. Let's try one more of those. 2 more actually. Again, drawing a picture is super helpful. So here we're told that we have minus 5, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. So we have those two vertices. And it says the minor axis has a length of 6. So 1, 2, 3, 1, 2, 3. So for this one, we have all 4 vertices, the 2 major vertices, the 2 minor vertices. The major axis is horizontal. So this one, we should be able to film pretty quickly. And it's centered at the origin. So the number under the x's, 25. The number under the y's, bless you, 3 squared. Nice. All right, the last one. Draw a picture. So the foci are at 0, 3, 0, 3, 1, 2, 3, 0, negative 3. And the major axis is of length 10. The major axis is in the same direction as the foci, so it's going to be vertical. If it's got length 10, it's going to go up 5 and down 5. 1, 2, 3, 4, 5. So that's the scenario that we have.
I have a question.
Sure.
How would we know if we just had the full side and the equal major? How do we know which direction the full side was going?
Say that once again. If we
How do we know which direction the full side, if it's vertical or horizontal?
So the foci are always on the major axis.
How do we know which one was the major axis?
Well,
On our graph.
we know it's going to be the longest one. So it's the whatever denominator is larger. So if the numbers under the y's are larger, it's vertical. And here they tell us that the foci are on 0, 3, and 0, negative 3. So they tell us.
Oh, obviously. Okay. Yeah.
So they're telling us that the foci are on a vertical line. So that tells us, oh, then our major axis must be vertical.
That's
That makes sense? Yes. Okay, so here we don't know how far left and right though yet. So we're going to say x squared over something plus y squared over something is going to equal 1. We can do the y's first. Those are 25. Now, we know c. C is 3. So c squared is 9. And 9 is the big denominator minus the small denominator. The big denominator is the 25. So 25 minus what gives us 9? 16. That's what's going to go there. So the big denominator minus the small denominator has to be c squared. So the big denominator minus the small denominator is 9. That means the small denominator is 16. Good. Any questions? Other questions? Very visual stuff here, these conics. Finding intercepts, moving around left and right. Very visual. Let's skip those. We'll skip that for now. Let's skip that for now. I want to get to the hyperbolas before we finish today. Let me put a ton of problems in there just in case. All right, so the definition of the hyperbola is way more abstract than the definition of an ellipse. An ellipse is pretty simple to conceive. You've got the distance to a point that's on the ellipse. It's got those 2 segments that have a sum that is constant. As you can imagine the arch and you can imagine the spring. And with a hyperbola, it's different. It's not nearly as intuitive. For a hyperbola, a point is on the hyperbola if the difference of the distances is constant. So if we pick a point on the hyperbola down here and we find the distance to this focus and the distance to that focus, the difference is a constant, whatever it may be. That's what the difference will be a constant instead of the sum. And that will create either a horizontal opening hyperbola, or you could have a vertically opening. Okay. The foci are always inside these arches. Foci are always inside. And the transverse axis is the axis that connects the two foci. So the transverse axis is right there. What section is this for? Oh, 10. 10.3. I just want to confirm that the transverse axis connects the foci and not the vertices. So the segment V2, V1 is the transverse axis. Okay, yeah, so that I stated incorrectly there. The transverse axis does only connect the vertices, not the foci. Without pass mustard. All right, right there. So that should say V1 to V2. Transverse axis connects the two arches. Okay. Complicated summary of everything. The hyperbola can open sideways or vertically, horizontally or vertically. Don't bother writing that down yet. We'll do the step by step to sort of break you in. All right. Now, what we did with the ellipse is the same way we're going to start with the hyperbolas. We started with intercepts. Very simple. We said, let's plug in x equals 0 and figure out y. Let's plug in y equals 0 and figure out x. Same thing. If we plug in x equals 0, what do we get for y? Plus or minus 1? 2. If we plug in y equals 0, something fishy happens. If we plug in y equals 0, doesn't that lead us to x squared equals negative 36? So what that tells us is that we have y-intercepts and no x-intercepts. Because x squared equals negative 36 doesn't have any solutions in the real numbers. Okay, so we have y-intercepts and no x-intercepts. But what we do when we look below, when we see that 6, we do in fact go out 6 both directions horizontally. And we don't have a point on the graph. But what we're going to do is build something called the fundamental rectangle. And the fundamental rectangle is going to connect those 4 coordinates, those 4 points, I should say. And that fundamental rectangle will have diagonals that are the asymptotes for the hyperbola. So we're going to draw these diagonals through the opposing vertices, which will then go through the center of the hyperbola. It's drawn right. Better. And this hyperbola will open vertically because it has y-intercepts. It doesn't have x-intercepts. It has y-intercepts. So it has to go through that vertex, and it has to approach those asymptotes. Something kind of like that. Not too crazy. Now, if it was an ellipse, if that was a plus in the middle, if that was an ellipse, it would just be like that. So it's really similar to the ellipses. You get those 4 points, but only 2 of them count. The other two are just guides to build this fundamental rectangle. Right? Now, the foci. The foci, we still look for c squared, but instead of subtracting the denominators, we add them. We do the opposite of that sign right there. So we add them. So we get c squared equals 40. So c is the square root of 40. That's 4 times 10, so that's 2 root 5. Huh? Did I say that right? Yeah, 2 root 10. Thank you. Four times 10. And the foci are always on the inside. This number is between 6 and 7. So it's going to be up here somewhere, down there somewhere. All that one have 1, all that one have 2. And if we wanted to write down the coordinates of the foci, we would say that they are f will equal, looks like the x value is 0, and then plus or minus 2 root 10. There's your foci. There's one other thing we have to find for an ellipse, for a hyperbola. The asymptotes. Asymptotes. Yeah?
1 equals 2 over 6x.
So we look at the fundamental rectangle, and we have lines, and we can see the slope pretty easily.
Or would it be plus or minus?
Rise over run, and we'd have to do plus or minus. So the rise is 2, the run is 6, so the asymptotes are y equals plus or minus 1. So it's up 2 over 6. 2 over 6 reduces to a third. Plus or minus 1/3 x plus 0. Y-intercept is 0. No? So a couple things to remember. For C, sum of the denominators. And the intercepts, there's only going to be 2 intercepts that count. And you'll start to see the pattern real quick. Whatever letter is in front of the minus, that's the direction that the hyperbola will open. So the y's are in front, so we're going to have y-intercept, so it's going to open in the y direction. Let's take a look at this one. Center, -4, comma 2. Go ahead and graph it. -4, 2. The center is right up in here. How far left and right are we going to go? From the center. Okay. Maybe I just do loose on this one and throw that thing. That distance is 10. How far up and down? 9. Go up 9. Down 9. If we wanted to label these points, from -4 we went to the right 10, so that should be 6, comma 2. From -4 we went to the left 10, so that should be -14, comma 2. Down here, we were starting at 2 and we went down 9, so that's -7. And then this one would be -4. And then from the 2 we went up 9, so that's 11. All right. Now, only 2 of them count. So think about that as I draw the fundamental rectangle. Only 2 of those dots are really on the graph. Which 2? Horizontal 2 or the vertical 2? The horizontal 2 are the 2 that are on the graph. That one and that one count. These are just guides. Those are just helping us to draw the fundamental rectangle. So then how do we get to our asymptotes? What's our next step there? Yeah, exactly, right? We draw the diagonals. X marks the spot, right through the middle. We draw these diagonals. We're supposed to go through the center and through the vertices, the opposing vertices. That's close enough. This graph is opening horizontally. These are the intercepts that mattered, or the points that mattered. Like that. Let's find the foci. The foci are found by looking at c squared. Do we add or subtract those denominators? Add them. So we get 181. That tells us that c is the square root of 181. I don't see any perfect squares in there. There may be one. I'm not seeing it. So that number is between 13 and 14. So somewhere out here, this foci, graph jump. So those foci are somewhere out in here. That's between 13 and 14. We're counting from here, though. Counting from there. We just put little marks, but we don't have to be super precise here. Call that one focus 1, call that focus 2. And the foci will have equation, or coordinates, let's see. The y-coordinate is the same as the y-coordinate of the center. So that part's the easy part. So the center we said was -4, 2. So we know 2 is the y value for both. All right, the x value is a little more complicated. We go to -4, and from -4 we're going right and left the square root of 181. Asymptotes. So we get our slope. You've got the slope on. So the slope is rise over run, plus or minus. And you can go back up here. The rise will be 9. The run will be 10. So that's plus or minus 9/10. Now here's the one thing that's different. We've shifted it. So we're not going through the origin anymore. So it's not just y equals plus or minus 9/10 x. We have to shift. So we're going to use the same terms that they have. They have y minus 2 equals and x plus 4. And that's how we'll leave it. We won't isolate y. We'll just leave it as y minus 2 equals plus or minus 9/10 times x plus 4. So this is the line, or the lines, with slope plus or minus 9/10, but then shifted to 2, -4. Let's do another one. All right, that guy. It's not quite in standard form, is it? The standard form requires us to have the right-hand side being 1. That's going to be the standard form. Go to our graph. Where's the center of this graph? 0. Yeah, 0, 0. So we are right at the origin to our center. How far up and down do we go? 3. How far right and left? So there's our fundamental rectangle. It will be a square this time. I think it's easier to do the rectangle. Okay, so there's our fundamental rectangle. It should be a square. The asymptotes will be right through the opposing vertices. All right, now which midpoints count? Which points count? Do we have x-intercepts or y-intercepts? We have y-intercepts because y is in front. If we plug in x equals 0, we get y equals plus or minus 3. But if we plug in y equals 0, we get x squared equals -9, which has no solution. So we have y-intercepts. And then we draw our arcs, they have to go through that point, and they have to approach both asymptotes. There's our graph. Foci, we need c squared. So we're going to take the square root of 18, that's 9 times 2, so we have 3 square roots of 2. And then that's foci, that number is between 4 and 5, so they're down here and up there. Oh, that one F1, that one F2. So the coordinates would be 0, comma, plus or minus 3 root 2. Right on the y-axis. Asymptotes. Y equals plus or minus x. Yeah. Because the rise and the run is 3 for both. Excellent. Let's try one of these abstract things. Abstractness. All right, again, picture. Picture is so helpful with these. So we have vertices, 1, 0, and negative 1, 0. We're going to put our vertices right there. Foci, 2 and negative 2, 0. So there and there. All right. We need our fundamental rectangle because we have no idea how steep this is or how sharp it turns. We need that guide. So right now, we're kind of unclear. It's a little ambiguous. We don't know how big this fundamental rectangle should be. So we're in trouble. All right. But what we know is that c squared is the sum of the denominators. Okay? Sum of the denominators. So we're going to use that fact. Should the x's come first or the y's come first? Do we have x-intercepts or y-intercepts? X-intercepts, so those are going to come first. So we're going to have x squared and centered at the origin. So right now we have that. And because the x-intercepts are plus or minus 1, we have just that. Don't know the y, but we do know c squared. C squared is equal to the distance to a focus is 2, so c squared is 4. So what has to go into the y's? 5 or 3? 3? I think 3. Because what do we do for the hyperbola? What do we do to the denominators? Add them. The sum of the denominators has to be c squared. So now that tells us that how far up and down are we going? How far up and down? Square root of 3. Square root of 3, so we're going to have to square root of 3, so let's move you down. Square root of 3 is somewhere between 1 and 2. So if we draw that very well. Great. Yeah. Somewhere between 1 and 2. Thank you. Somewhere between 1 and 2. That's good enough. So then we're going to do diagonals. Through the vertices, and should go right through the center. This thing will open sideways then. Oh, I guess they didn't ask us here. They were just saying find the equation. All right, so there's our equation. Now, it doesn't ask us to find the asymptotes, but we could find them pretty easily there. Rise over run. I want to do this one now. Okay, so here they tell us the asymptotes and they give us one vertex. And we want to try to come up with the whole equation. So let's draw a picture and see if that sketch will reveal what we need it to be, what we need. So the asymptotes are right through the origin, right? So that tells us our hyperbola is centered at the origin. And it tells us one vertex, 0, 3. So if that's a vertex, and it's centered at the origin, then there's another vertex down below. And now the asymptote's minus 5/4. So from the origin, we're going to go rise over run. So up 5 over 4. I'm going to go up 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. Over 4. Over 4, so it's right there. So this asymptote goes like that. There's going to be one similar like that. Okay. So this is y equals 546. The fundamental rectangle is trapped a little bit lower though, right? Isn't the fundamental rectangle going to be like right in there somehow? The fundamental rectangle's got to go through those two blue dots. We don't know what the lateral constraint is yet. But what would tell us is this. We know that the y value right there is 3, and what we're trying to find is the corresponding x value for a y value of 3. So we're going to plug in 3 and try to figure out what x is. So x will be 12 over 5. So 12 fifths. So 12 fifths is 2 and some change. 2 and 2 fifths. So we've got pretty things there. Not great. Pretty things. Okay, so the equation then, what is the equation? So we have y's are first, so we have y squared over 9 minus x squared over something equals 1. So what should that x, what should be under there? Not 3. So the x value that we just found was 12 fifths. So 144 over 25. We have to square that thing. 144 over 25. And so if typically what they would write this as then, they would pull that 25 into the numerator. That would be written like that. Yeah, so once we find that x value over there, we just square it. Because the denominator is that distance squared. The other way to think of it, once we have that in there, we're going to go left and right, the square root of the denominator, so we're going left and right 12 fifths. Good? All right, let's stop. Let's have a big, long, steady session. I mean, break. It is actually snowing outside right now.
Yeah, it is.
What's that?
According to my girlfriend, it is.
Yeah, this is yeah. Cool. Our first snow. We haven't even had any precipitation in like so long. Oh,